Hello everyone, my name is Franz Wotawa and I'm happy to give you the presentation of our paper entitled Checked Coverage for Test Suite Reduction, and we are going to answer the question, is it worth the effort? This is joint work with my colleagues Roxane Kreutz-Ristov and Lukas Stracke. Lukas Stracke is a former master student of mine, and he basically designed, developed and made this framework I'm going to present today available for you. So all the credits basically goes to him. What is test suite reduction and what is checked coverage? So these are the things we are going to discuss first. And let me motivate what we understand about that in there, and also about the practical importance of test suite reduction. Let us consider a program, a system that is under development, or where we may have one or two or more releases available, and in each of these releases, in each of these new versions of a program, there are test cases introduced. And of course, as a consequence, usually, finally, what we get is a huge number of these tests, especially when the program is becoming more and more mature, then we have a lot of tests. Some of them are, of course, covering important features. We cannot ignore them. Some of them may, let's say, discover the same features again. And so what we want to get rid of is basically all the redundant test cases. But still, what we also want to do is not to decrease the potential for detecting faults. So we don't want to decrease the fault detection capabilities of the test suite. And this is very much important. When we are removing a test case like this, test case N, then we still want to find a bug in the program, in the system under test, when we are going to execute it using the other test cases. So basically it has to deal with, we have to deal with redundancy elimination, and this is the purpose of test suite reduction, to get the smallest number of tests that still reveal buggy behavior in a program we have. So let us go to the content of my presentation today. First of all, we will define this test suite reduction problem more formally. We will answer the question how to judge these fault detection capabilities of a test suite. That seems not to be that obvious. Afterwards, we're going into the framework that is the basis of our experimental analysis. Afterwards, it's called Java Test Suite Reduction Framework, JSR, and it's available as open source software for all of you. Please contribute to this effort in here. Finally, we'll discuss the experimental evaluation, answering the question whether checked coverage is worth being carried out. And I'm going to summarize, of course, all the findings finally. Okay, so let's jump into the foundations. So foundations, of course, are dealing with the test suite reduction problem and the fault detection capabilities. Let's start with test suite reduction. So there is a nice definition by Gignot and Mark Harman, and in this definition we see that the test suite reduction is based on a test suite, of course. This test suite comprises T1 to Tn test cases, and we also have requirements R1 to Rm for this test suite. And the interesting thing is that for each of the requirements we have a corresponding set of test cases, and this corresponding set of test cases are all those tests that satisfies the corresponding requirements. So in Ti, basically what we have is that all the test cases of Ti satisfies their corresponding requirements Ri. And the test suite reduction problem then there is, of course, to find a reduced test suite T prime that contains the tests from T, of course, and still all the Ri, all the requirements are satisfied by at least one of these tests. So, and finally, of course, what we want to have is that the number of test cases in the reduced test suite is minimal, which means the smallest number in here. So that's cardinality, minimality, as I would say as usual, but as often used here in this case. But still, we want to fulfill all the requirements given. And the question, of course, is what are the requirements, how to find this test suite, and so on. And so let us consider all these cases here in a row. So first of all, we have to find this reduced test suite fulfilling still all the requirements. How can we do that? There are several methods reported in literature. I don't want to go to all of these methods in detail and give you all the references. Some of them are in the paper, so the recommendation here is to take a look about these references. Nevertheless, we can distinguish at least three different type of test suite reduction methods. One is a search method that basically is going through this whole search space where we pick test cases, check whether they are fulfilling the requirement, and we are doing so until we have a selection of test cases, and then of course we are minimizing that in here. So search here means trying to find this minimum number of test cases that still fulfills all these requirements. Then there are clustering based approaches which may apply clustering methods that help us to find let's say this minimal set easier. And then there are methods that are using basically heuristics, greedy algorithms. There are also search-based algorithms to some extent, but based on heuristics, where the heuristic is basically saying, for example, that we should select test cases first that covers most of the requirements, and afterwards we are selecting the next one that covers the next most number of requirements, and so on. Heuristics usually are not leading to the minimal results, not like in an ordinary search procedure where we don't use heuristics. So really want to have a precise minimum set of test cases for this reduction problem. But of course they are usually faster because the decision for choosing tests can be done locally, and so they are usually the best cases here we can have. Why the best cases we can have? Because this test suite reduction problem is known to be NP hard, and the minimum set cover problem is the related problem we have to consider here. So an NP hard means, of course, some exponential runtime, and therefore heuristics make sense because they are usually reducing this runtime substantially at the cost, of course, of not finding the minimum test suite in here. We can categorize this algorithm in either adequate or inadequate ones. Adequate ones means that of course all the requirements are fulfilled, so there is a guarantee that we are fulfilling these requirements, or inadequate whether there might be a test suite returned that does not fulfill all the requirements. So what we want to have here basically is of course adequate algorithms, but maybe we are less interested here in always obtaining the smallest reduced test suite to be practically relevant in here. Okay, so this is the test suite reduction problem, and you can let's say imagine what the requirements are saying. The requirements basically are saying that some fault detection capabilities might be respected or not. And so what we go in here in the next step is discuss what we understand about fault detection capabilities. So first of all, start with a remark. So the question here is basically, when we remove a test suite, like mentioned here, is a previously revealed fault still in there? So that's basically the underlying idea about fault detection capabilities. So we want to have the test cases that potentially identify tests that fail, basically, okay, when we are executing them. And of course, what we always want to have is a reduced test suite that still is able to detect the same faults than the original test suite. And so the question is, how can we determine this potential of fault detection for a test case? Okay, and one idea here that makes use of the assumption that the more code we see being executed, the more code is executed, the more likely a failure is revealed. So this is the underlying assumption. And so what we can do is we can make use of source code matrix in here when carrying out or source code matrix, a matrix based on source code and source code execution, the executed source code to be more precise, when carrying out a test. So this is coverage information. Most of you know that, and this coverage information is based on this assumption that the more source code we are carrying out, the more likely we identify a fault. It's not a let's say an absolute condition that we of course when we're executing source code that it is guaranteed to find a fault, but it's at least some requirements we have to have, because something that is not executed will never reveal a bug in here. So what is source code coverage for your information? And to be very brief in here, there are various definitions, of course. Basically, they are all used for judging the quality of test suite. Basically, it's saying the higher the coverage is, the better is the test suite. And the idea there is as follows. So let's consider here this test case. When we are calling the test case, this test case is executing this is even for function. Then of course this function is executed. When this function is executed, then we say, for example, this method, this function is covered, and that's basically method coverage or function coverage. It's basically saying, okay, how many methods do we have? How many methods are covered when executing the tests? And if we are dividing this number, then we get the method coverage. What happens when we are executing these methods? Of course, it's executing the second statement because it's at the beginning here. It's then going to the if statement. The if statement in this case, or the condition would allow us to go to the 10 branch. So we are executing this statement here. The result is true, and counter even plus plus. And finally, of course, we are leaving this program. And all these statements I have marked now, they are the lines that are executed. And if this is the whole program, then we see from 16 line, we have basically executed, okay, we have executed the tests, which means 14 and 15. And then we have executed third, fourth, fifth, sixth, seventh, 8 statements. So from 16, we have executed 8 statements, which means 50% coverage for this test case. Again, it's the number of lines executed and divided by the total number of lines we have in a program. So this is line coverage. Of course, there are more sophisticated coverage methods like MCTC coverage, decision coverage, and whatever. All these are used in practice for safety critical systems, for example. But of course, they are harder to compute. Line coverage and method coverage can be easily computed. And how can we carry out this? Of course, we are executing each of these test cases, and this is the nice thing we have in here, and that's the reason why we get in this coverage information. And so we are summing up basically all the statements that are executed. However, what we also saw in the test is that there was an assert statement in here. I will go through an example in the next slide. And this assert statement basically is implementing a test oracle. And what is a test oracle? A test oracle is basically a condition that has to be fulfilled. So in a test, we are running a program, we are running a method, whatever, and then we are checking whether the test oracle is fulfilled. And this is important, of course, because it allows us to judge whether a test is passing or failing. So this is what we have here. And for each of these tests, usually we have this test oracle. Why I'm telling you that? Because the coverage information before was not considering basically the test oracle itself. It was considering the tests that were the statements that were executed when running the test, but not whether a test oracle still was, let's say, necessary, or the condition that is defined here, was important to judge the quality or the outcome of the test in here. So we may want to know which statements contribute to the value of the checks by any of these test oracles. So the rationale here is that the statements that do not really contribute to this condition are not really checked by this. They're executed, but they're not checked by this oracle in here. And so here we see that the ordinary coverage, statement coverage or method coverage or whatever, they do not really judge the quality of a test case in here. There are at least ignoring these test oracles. And so when we are really able to judge the quality of a test oracle as well, we are going into checked coverage. And checked coverage basically makes a dynamic slice of the condition in the test oracle and takes those statements that are in this slice and executed, of course, as a measure for coverage. Let me go back to this example where we have this is-even function and the test oracle. What we see here is that we have here some control dependencies. Of course, when calling the is-even function here, we are going to this static Boolean is-even function implemented. Then we see that we have here, of course, this integer variable where we have a data dependency here because it's num to this statement here. Because of this statement here, we see a condition, control conditions in here. Result is true, therefore we have a data dependency to these results here. And of course we have then also a data dependency from results, because this is basically what we see here, what is checked in here. And what we see here basically is that in this case also the mentioned statement are depending on these assignments, so they are included in checked coverage. And the definition of checked coverage is basically the statements that are necessary to get a value for an assertion and that are executed, of course, as well, and divided by the total number of statements of lines in the program. So usually checked coverage, of course, is a little bit, let's say, harder, containing a little bit less lines of code than line coverage, but is at least going into the same direction. We need slicing for these, and you will see that this has an effect, of course, on the outcome in here. So how can we use now coverage for test suite reduction? It's basically that each requirement basically states that a particular line or method is covered by a test case. So these are the requirements we have, and then of course all the test suite that are covering these particular lines are in this set TI in here. And so we have here for each requirement a corresponding test suite, and this test suite, of course, which is a part of the original one, covers this line of methods and allows us to use the definition we had before. So let me now go briefly into this Java Test Suite Reduction Framework, JSR. The objectives have been to provide a platform for integrating this TSR in practical software development, in the workflow there, to allow, of course, extending this framework easily. There are a lot of functions in here, and to be of use here for research. And basically what I'm going to present are the results of or one part of this research. It's open source, and here you find the link in here. So please feel free to use that for your research as well. So what are the features now? It's basically currently implementing 3 algorithms. It's a greedy algorithm, a delayed greedy algorithm, and a genetic algorithm, a simple one. It handles the JUnit 4 testing infrastructure, so it's for Java. It's basically considering at the moment 3 different coverage metrics, which are checked, line, and method coverage. And of course, because of Java, it's platform independent, so it can be used in here. The workflow is as follows. So we take the SUT, the Java program, convert it into an internal representation, take the codes here for the test suite, which are the JUnit 4 tests, make an internal representation, compute the coverage then using certain tools, getting a coverage report out of that, using that for reduction, getting a reduction report out there, and then of course a reduced Java code comprising only those statements or those testing statements that are important for us. From the architecture, as I said, it's open. It comprises a core functionality everyone can use, and also an IDE plug-in you can use in here, as well as a interface to a command line shell, a command line interface, what we have in here. So you can either use it as a plug-in for some IDEs or in a patch file as well. The core itself comprises, of course, parsers, coverage calculators, some reduction algorithms, as said before, code generators, and makes use of external tools like Jacoco and Slicer4j for providing us with the required coverage information and slicing information. There are a lot of dependencies in here. Everything when you want to install that in there is, of course, the information is provided, so you will find that easily in here. Let's jump to the experimental evaluation. So what are the prerequisites there? First of all, as said, we have these 3 algorithms. We have here this greedy algorithm that uses an heuristics, which are favoring hard to fulfill requirements. As said before, there is not a requirement, or it may not lead to an optimal solution. However, in many cases, it's quite a small test suite. We also implemented delayed greedy, which is basically greedy with a combination of reduction rules. The reduction rules are first used for reducing a test suite, and afterwards there is a step, a greedy heuristic step in here, and this usually leads to a test suite that is I won't say close to minimal, but usually a little bit smaller than for greedy. And then we have this genetic algorithm using a certain fitness function that is based on the TSR requirements. So the fitness is -1 if a certain test case G is not covering these requirements, and otherwise it's the maximum here of 1, and other values that are using the information getting from the coverage tools in here. We use mutation probability of 0.4 and crossover probability of 0.15. Of course, this can be changed in the tool, but that was what we used basically for the experimental evaluation, and for the initial population it was 5 times the number of the test cases. I don't want to go into detail about these algorithms. There are links to certain papers, of course, available also in this paper in here. What else have we done? We have carried out the test suite or the test suites of available benchmark projects, and they are basically also open source projects with various numbers of um, JUnit tests provided. Of course, we selected those where there were JUnit tests in here. What you see here is for the lines of code, we are varying from, let's say, larger programs, almost 70,000 lines of code, to smaller programs of about 400 lines of code. And you see also that for the tests, we have partially quite a lot number of tests or program lines that are required for implementing these tests. And here you see then the number of test cases in total. So we checked, of course, that there is a larger number of tests available. Here we see also then the original coverage scores when we before reduction using all the tests we have in here. For checked coverage, the information ranges between 0.75 and something about 0.4, around 0.4. For line and method coverage, we have higher coverage information, partially leading to 1, but not always, of course. Like always, there is always code that may not be executable because it's dead code, or is not covered by tests because it's not really used in here. Okay, so this is the prerequisites regarding the programs and test suites we are using. We also we run all the experiments on an Intel Core i7 with, I think, with a standard RAM configuration, so it was an ordinary computer here. We detected also, interestingly, zero coverage test cases that are test cases that have not any coverage information, which is quite interesting. Here, of course, maybe some tests are not having a cert statement because they are used for other purposes. Sometimes, of course, instead of assert statements, there are other statements used in here, and so we were not able to make use of that. And so we have carried out this evaluation considering these zero coverage test cases, and also, of course, not considering these zero coverage test cases. In the evaluation, we wanted to carry out or giving out you answers about two research questions. Research question 1 is checked coverage a suitable DSR requirement criterion, and how does it compare to the other coverage metrics we have here? And our research question 2 is which combinations of coverage metrics and reduction algorithms performs best with efficiency, of course, and effectiveness, which means reduction capabilities. The interesting thing here is the random information required for computing coverage. What we see here is that checked coverage, of course, takes most of the time, on average 8 hours, compared to the other versions where we have 7 minutes on average for line and method coverage, because that's the time required for carrying out all the tests. And let's us jump into the results obtained, and then we have a look at the research question. So first of all, we have a look at the greedy algorithms. For the greedy algorithms, what we see here is a varying number, of course, depending on the program, of reduction in here. So these numbers means the more the better. What we see here on average for check coverage is 0.66. For line coverage is 0.577. It's worth noting that we have not considered the zero coverage test cases for these. And for method coverage, it was larger. So what we see here, basically, that the reduction for method coverage is best, but method coverage is also a weak coverage criterion. Checked coverage beats line coverage, at least to a minor scale. And when we compare the greedy with delayed greedy, we see a higher reduction here, a little bit higher reduction here for the different coverage criterion. So delayed greedy seems to provide smaller test suites in here. The situation is worst for the genetic algorithm. It delivers basically the worst reduction when compared with greedy and delayed greedy. And here again, we see that checked coverage performs quite well. Interestingly, method coverage is not first in this case, but second. And but still, there between checked and line coverage, we see this picture here, even in the case that let's say the average values are quite low. Again, for zero coverage test cases, when we are introducing these zero coverage test cases, we see a different picture. We see that this factor, the reduction factor, decreases substantially. So it decreases really to 0.548 instead of 0.66 we had before. So what we see here is then that checked coverage drastically falls behind. And of course, we can put that into a more general picture, considering this reduction factor distributed among the different methods and algorithms. And what we see here, so this is with zero coverage test cases, and for that it's without in here. What we see here is that the checked coverage with considering the zero coverage test cases falls behind line coverage basically and method coverage, and that's basically for all the, or at least at average, for all the different algorithms we have in here. There is also a very nice measure for let's say judging the quality of test suite, and that's the mutation score, where we introduce faults, and the question is whether these faults can be really found. And here we see results we obtained from the mutation score distribution in here. This was the mutation score for the original test suite, and when we have here checked coverage with considering as well the zero coverage test cases, then we see there is a drop in here in the mutation score. We see it for all the things that there is a drop in here. However, for line coverage and also for the other algorithms, we see that this drop is at least the least in here on average. And so we see here that line coverage retains quite well the capabilities of detecting faults, which we can here map to this mutation score in here. So the capabilities of finding faults that we may not see here and may not have not considered is quite high for line coverage. So when we summarize these findings as follows, we can answer the research question. And what we see here is that check coverage is a suitable matrix. Nevertheless, it's basically outperformed using line coverage. Why? Because it's faster to compute and has also a lower fault detection loss we see with the mutation score in here. Moreover, computation time for check coverage is very high, so it might be not very much practical, especially when considering larger programs. So check coverage is fine, it's a good idea and a nice thing here, but line coverage, which is easier to compute, is still a good, let's say, a good matrix in here, and maybe better than checked coverage. Line coverage performs best. On average, of course, greedy algorithms are quite good. They have fast computation time and better reduction, and this is what we want to have here often. So let me conclude now my presentation and summarize all the findings. So the tool is available, you can use it. We compared here 3 different algorithms on 3 different coverage metrics, and we presented the experimental results obtained considering 10 open source projects. And what we see here is the checked coverage has a high runtime, no superior reduction, and I would say not so well mutation score. So in the fault detection capabilities, there is a reduction we see in here. So line coverage performs more or less best in our study here. So thank you very much for your attention, and I'm ready to take questions.